is happening. The sulfur attacks at the carbon. Remember we said methionine is not terribly reactive, but it will go after cyanogen bromide. So there's a nucleophilic attack by the sulfur from the methionine on that partially positive carbon. So you get that little adduct there, and then it cyclizes, okay? And you get this. And then you can cleave with water here. What is that? It's a CN double bond. It's an imine, okay? And you get cleavage there to get this. Now, what do you call this? It's cyclic, okay? And it's an ester. So what's a cyclic ester called? A lactone, exactly. And notice that someplace here, it gives you what's called a homoserine lactone. You know the lactone, that makes sense. What about the homoserine part? What's a homoserine? We haven't considered that. Serine, of course, looks like that, okay? What if you had an extra carbon down here? What if you have this? We call that a homoserine, okay? That's a homoserine with one extra carbon, an analog of serine, but one extra carbon. So if you have a homoserine that forms an ester with a carboxyl group, you would have that. So we call this a homoserine lactone. Now, let's go back, think about that reaction, and go up back to our peptide, and think about a peptide that has something like that in it. So here's our protein, or peptide, whatever. And this is a COO minus. And let's put a methionine in here, okay? And say we get cleavage there, okay? What do you get? You get one peptide with a homoserine lactone, and this part's still going to be an NH3+. And the other peptide that you get is going to be a conventional peptide like that. So cleavage with CNBr at a methionine gives you two peptides, one of which contains a homoserine lactone. So when you're working the problems in the back of chapter 5 and you treat with cyanogen bromide and the clue says there are two fragments, one of which is a homoserine lactone, then you know that was the front end of the protein or peptide, the leftmost, the N-terminus of it, and this is the C-terminus from a methionine cleavage with cyanogen bromide. Does that make sense to everybody? Question?
So like with a slide like this, like preparing for a test, like if we understand what you just wrote on the board, and you really get that to the back of the questions in the book, like if we understand that, is that sufficient, or do we need to know like the mechanisms? Like I don't understand what's expected of us.
Well, that's a good question. I won't expect you to know the mechanism, okay? But I do expect that you know what you get. And to figure out what you get, it's worth looking at the mechanism. That's why it's here. So the mechanism is to show you why you get this, okay? And all I really need you to know walking away is that that is what's left of the methionine. Look at the coloring. See the green carbons there? And the green carbons here, okay? That shows you that those two CH2s ended up in the product. Okie dokie? How's that? So the mechanism is relevant to show you what you get, but all I really want you to know walking away from this slide is cleavage with methionine gives you a this and a this, okay? One normal peptide and one with a homoserine lactone at the C-terminus. But you got to know why that happens, so that's why that's there. Is that good for everybody? If I just said CNBr cleavage gives you something with an HSL at one end, you know, that's not going to make a lot of sense. So that's why we walk through that. Okay? Okay. Good enough? Any other questions about that? Okay. Onward. So now there is the overall reaction. Okay? CNBr with a polypeptide gives you a C-terminal peptide. That's this part, and a peptide with a C-terminal homoserine lactone. That's this part. That's the overall for this, okay? Makes sense to everybody? Good. Okay, onward. Back to this table again. Now we've covered everything you need to know. We've talked about trypsin, chymotrypsin, clostrepane, staphylococcal protease, and CNBR, okay? So don't memorize that chart. Don't memorize the table, but know what trypsin does, what chymotrypsin does, and so on, and also what cyanogen bromide does. How's that? Is that pretty good? Yeah? Agreement? Disagreement? Questions? Quiet today, my goodness. Yes?
You may have already touched on this, but just to clarify, all the other ones besides cyanogen bromide, they're just creating just a split in the chain, but no modified amino acids.
They're cleaving the amide bond, and they're leaving you with a carboxyl on the left and an amino on the right. That's exactly right. That's a good and a fair question. That's absolutely right. Yep. All the others are just cleaving an amide bond. And what do you do when you cleave an amide? You get a carboxyl and an amino, right? Is that good? So yes, all the others give a normal pair of peptides, one with a carboxyl at the point of cleavage and one with an amino at that point of cleavage. How's that? Is that fair? Better? Getting better? A little more nodding would be good? Okay, fair enough. I hope that's okay. Hope it makes sense. So now, step 6. This is the big moment because you're reconstructing the sequence. This is solving the Humpty Dumpty problem, okay? Use 2 or more fragmentation agents in separate fragmentation experiments. So you have one tube where you cleaved maybe with trypsin and one tube where you cleaved with cyanogen bromide. 2 different samples of the original protein. Get a set of cleavages here, a set of cleavages here. Then you have to compare the fragments to see what overlaps with what. Okay? Sequence all the peptides that you get, usually by Edmond degradation, okay, the phenylisothiocyanate. Compare and align the overlapping peptide sequences to learn the sequence of the original peptide chain. Is that good? So here's how it works. Here's an example. Let's say you do trypsin cleavage of some unknown peptide and you get AEF and so on out to K for one peptide and LVGK for the other one. You say, great, I can put that back together and know the original sequence, except you got Ks at both ends. What's K?
Lysine.
Lysine, good. So you got 2 lysines. Trypsin cleaves at lysines. So one of those is a cleavage point. The other one is the end of the protein, right? So you had a protein like that, where this is a K, and there's a K in the middle. So you cleave and you get this, and they both got Ks at the end. So now what? So you do a different cleavage. You use staphylococcal protease, which cleaves where? Go back to our table. Where does staphylococcal protease cleave? Asp glue, exactly. Okay, so now you have a protein that's going to cleave at an asp or a glue, and you look at this and say, good, there's a glue, thank goodness. There's the cleavage point for that second experiment, and there's a K. It couldn't have cleaved there. So you know that this piece goes over here, and so you know, looking at the overlapping fragments, that the correct sequence is LVGK, AES, and so on out to K there. So now you understand that trypsin would have cleaved here, and that's just the end of the protein, okay? And you could have done that just with the staphylococcal protease, but just to show you how this is done, it's a really simple example to sort out, okay? And then you can look at way more complicated experiments, okay? And this is a protein called catracolistatin, and it's a large protein. It's got many cleavage points, and you can see all the different fragments that have been generated by various cleavage techniques here. And you can see that there's lots of places where things overlap. And you can see, for instance, that this and that are similar sequences. So you know how to put this peptide overlapped with this one so that you can align things. Yes?
So I'm a little confused when
Okay.
it says sequence all the peptides produced with Edmond degradation.
Uh-huh.
You were saying that's only viable to pull off the very first amino acid.
No, sorry. When you do N-terminal analysis, you want it to get 1, and then you're left with a sample that's missing 1 amino acid. Then you treat with another equivalent of Edmonds to get the next residue. So let's go back, in fact, to this case, okay? Let's say you did staphylococcal protease cleavage. So you get these two fragments, but you haven't sequenced them yet. So now you apply Edmonds reagent. You get one residue here with one equivalent of Edmonds, another equivalent here, and get the serine, one more equivalent, and the next experiment you get a glycine, then you get an isoleucine, then you get a threonine. But these are all separate additional experiments. You do the cleavage just to get a small fragment, and then you have to sequence one residue at a time with added amounts of Edmonds reagent. So you start with a peptide like this. Let's say you separate this and this. So you just have this in a test tube. You put in one equivalent of Edmonds and you knock off a phenylalanine as a PTH derivative. You run that through a column with standards and you say, oh, that's a phenylalanine PTH, or a PTH phenylalanine. And then you do another equivalent of Edmonds and you get a serine as a PTH derivative, run that through the column and say, oh, that's a PTH serine. Then you treat again with Edmonds and get a G, a glycine. So that's a PTH glycine. You run that through the column and you characterize it. So you get the idea. Does that make sense?
Skip the step of cleavage and do that for the entire sequence.
For a short one like this, you could. But what if it's 100 residues long? What happens then? Is a really good question. So I said before that you can only do about 25 residues at a time before things get messy, and here's why. Despite your best efforts with a protein of some undetermined sequence, let's just say it's like this, and let's say there's 80 residues, okay? Let's say there's 80. So you take your 80 residue peptide and you start doing the Edmonds treatment one after the other after the other. And let's say you're 90% perfect with that first residue. That is to say, you get 90% of the peptides to give you a phenylalanine, okay? And then you treat with another equivalent of Edmonds, and you get 90% of the protein to give you a serine, okay? And then you do another treatment, and you get 90% of them to give you a glycine. What are the other 10% doing? The other 10% are either not reacting at all, or they're taking 2 amino acids off when you only wanted 1. So you get what's called noise in the experiment, okay? So let's just do this. We'll be very visual. Here's 5 molecules of your unknown protein, okay? And let's say it's phenylalanine and what we say, serine and glycine all the way along. Okay? And let's say 4 of those cleave exactly right when you treat with one equivalent of Edmonds. What's that other one do? Perhaps it didn't react, okay? And so the next treatment with an Edmonds is going to give you 4 of the 5 yielding a serine, and this one yields a phenylalanine. You see the point? If this one didn't react in the first treatment, but it does in the second, you're going to get a phenylalanine to confuse you because everybody else gave you a serine. And then let's say you do this again, but let's say this time that this one doesn't react, okay? And so you get cleavage, 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 cleavage. And so what do you get for that second treatment, or third treatment rather? You get, we were doing this one. No, we're not doing this one. So this one does nothing on the third treatment. We'll just go like that to say nothing came out. This one gives you a glycine, that gives you a glycine, that gives you a glycine. What does this do? Maybe this one didn't react the first time, so this time it gives you a serine, okay? So now you have 3 of them giving you a glycine, 1 giving you nothing, and 1 giving you a serine. And now you do a third treatment, okay? And you get a glycine this time, and let's say the next residue is an E. So now the 4th treatment gives you E and...
You already cut that one.
Oh, we already cut that one. That's right. So you get the G there. This time you get E, 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 and now you get a G, for example. These noise factors build up. And after about